not only is it important to know the measure of central tendency that best represents your variable, it's also critical to know the variability. The variability tells you the spread of the values that you have in your data set. Variability is related to reliability, and we talked about reliability in an earlier lecture in this module. So there's three measures of variability. There's the range, there's variance, and then there's the standard deviation. We have talked about the range before in a previous lecture. The range is just simply the difference between the extremes of exact values. So in other words, all we're really saying is the highest value minus the lowest value. And we've talked about that before when we talked about range versus full range. So the thing you need to remember here is that when we're trying to get an estimate of variability, we're going to calculate the range, the difference between the extremes of the two exact values at the end of the scale, the highest value and the lowest value. Now if we're trying to create a frequency table, then we're going to use the full range, because in order to create a frequency table, we need to account for all values in our data set or in our variable. And so if we're making a table for a frequency table, then we are going to use the full range. If we're just getting a measure of variability to go along with our measure of central tendency, then we will use the range. The second measure of variability that we'll talk about in this class is called variance. Again, variance is another measure of reliability. In particular, variance is an indicator of the spread of the values. So much like reliability, it tells us just how spread out the values are. However, variance accounts for differing values from a particular set point. Now that set point is going to be from the average. In other words, the set point is going to be the mean as a measure of central tendency. And so by definition, variance is the average squared deviations from the mean. And so there's a lot of words there, but that actually is the formula, and we'll have symbols for it here in a second. But the variance is the average squared deviations from the mean. So when we get a number for variance, it's telling us the average difference from the mean in squared units. So here is the formula for variance. Now variance is going to be represented by the lowercase Greek letter sigma. In particular, sigma squared, because remember, variance is the square deviations from the mean, or the average square deviations from the mean. And so we'll indicate it by a square, and the symbol we'll use is lowercase sigma. So when we use lowercase sigma, being a Greek letter, what we're saying is that this is the formula for variance for a population. And we know that because our symbol is a Greek letter. Now the remaining symbols in our formula you've seen before. We saw them when we calculated the mean, when we're getting our measure of central tendency. The next symbol in our equation is capital sigma, so it's a capital Greek letter. Being a capital Greek letter, it actually doesn't indicate population here. It indicates an operation, and that operation is to sum. So we'll sum up whatever follows this symbol, capital sigma. In particular, we're going to add up everything that is within this parentheses that follows that sigma. So let's look at those symbols here. You've seen x before. X just represents each individual value that is in your data set. So we'll go through each of the individual values. We'll take those individual values and we'll subtract something from it. In this case, we'll subtract the mean of the population. So notice the symbol is mu. It's a lowercase Greek letter. It represents the population average. So we'll take every single observation and we'll subtract the mean from each of those observations. Once we do that, we will then square it. So we'll take each observation, subtract the mean, we'll square that value. We'll do that for all of the observations in the data set, and then we'll add them up. Again, capital sigma. Now once we have added up all of the squared deviations from the mean, or in other words, each value minus the mean squared summed up, that'll give us the numerator. We will then calculate an average by dividing by the number of observations. So if you remember, capital N tells us the total number of observations that are in our variable, or the total number of values in our variable. And once we do that, we then have our variance. In other words, we have sigma squared, the average squared deviation. Now let's walk through the calculations with an example. So let's say we have little Timmy here, and we want to know just how much Timmy appreciates his family. So we'll say his family is the population. And so for Timmy, we'll ask him on a 1 to 10 scale how much he appreciates his brother, his dad, his mom, and the family cat. And so we go to the brother. He says on a scale of 1 to 10, where 10 is the greatest, his brother gets a 3. We ask him about his dad. His dad gets a 7. his mom gets a 10, and the family cat gets an 8. And so we have 4 observations here. We have 4 values that represents Timmy's appreciation for his family. So go ahead and take a moment, pause the video, and calculate the mean for little Timmy's appreciation for his family members. So in order to calculate the mean, you had to calculate what n was. And again, n is the number of observations. So in this particular case, there are 4 members of Timmy's family, and so our n in this case would be 4. And so if we wanted to get that mean, we would take our 4 values for each of the members of the family, and we'll add them together. So 3 plus 7 plus 10 plus 8, we end up with 28. We then divide by the total number of members in the family, in this case 4, and so we should have got a mean of 7. And again, n, our population size in this case, would be 4. Now let's go ahead and calculate the variance. We will walk through this together. So here's our formula. We have sigma squared equals the sum of each value, or in this case, each rating of each family member, minus the mean, squared. The sum tells us to add it together, and that's the numerator. And then we divide by the total number of observations, in this case 4 observations, or 4 members of little Timmy's family. So we should take a moment and talk about order of operations. So whenever we're calculating with formulas, we want to look for parentheses first, and if we see them, we want to do what's in parentheses before we do anything else. Following parentheses, we then want to do multiplying or dividing, and then once we're done with that, we then want to look for adding and subtracting. Now if we have a ratio, in this case we do, we have a numerator and denominator. We want to do what's in the numerator first, and then the very last thing we want to do is what's in the denominator. So here we'll start with the parentheses, and we'll start with x minus mu. So we'll take each individual value and we'll subtract the mean of the population from each of them, and that will give us a deviation score from the mean. So here we are. Here's each of those scores, 3, 7, 10, and 8. The mean is 7. So we'll subtract 7 from each of those values. So remember, x minus the mean, x is each of the original values. We subtract the mean of 7. So we'll take 3, we'll subtract 7. We get a deviation score. That's what that column that says DEV stands for, deviation. We get a deviation score of -4. 7 minus 7 is 0, 10 minus 7 is 3, and 8 minus 7 is 1. And so we have a column of deviation scores that represent the subtraction of the mean from each of the values. Take a moment and pause the video and add up all of the deviation scores. So in other words, what happens if we sum the deviation scores? Now if you added up all those deviation scores, you should have ended up with 0. So if you took -4, added 3, added 1, you would have got 0. And that's always going to be the case whenever you take the mean and subtract it from your original values. The reason for that, if you remember back when we talked about measures of central tendency, the reason for that is that the mean is the balancing point. In other words, all the values above the mean cancel out all the values below the mean. And so we're left with a perfectly balanced scale. Once we have all of our deviation scores, in other words, we've taken each value and we subtracted the mean, we then want to go ahead and square each of those scores. So here is our data again. Notice we've added a new column, SQU, which stands for squared. So we took each deviation score and we squared it. So we took -4 times -4, and we got 16. 0 times 0 is 0, 3 times 3 is 9, and 1 times 1 is 1. And so now we have a column of deviation scores squared, or what we call. Once we have our squared deviations, we then want to sum it. And so that's what the sigma, the capital sigma here, tells us to do, is that we're going to add all of those squared deviation scores up. This is what we call the sum of squares. And we'll see the term sum of squares throughout the remainder of this semester. When we say sum of squares, all we're really talking about is the sum of the squared deviations, where we take each value minus the mean. Okay, so we have our squared values. We want to go ahead and add them up, because remember we're summing them. So we'll take 16 plus 9 plus 1, and we'll end up with 26. So that's the numerator in our equation. We have sigma squared equals 26 divided by n. And if you remember, n is the total number of observations in our data set. So in this particular case, little Timmy has 4 other family members. He provided a rating for each one of those family members. So we'll take 26 and we will divide by 4. When we divide by 4, we end up with 6.5. And so our variance is 6.5. The average squared deviations from the mean is 6.5 squared units. So we can expect that any particular rating that Timmy has for any member in his family will be 6.5 squared deviations from the mean. If you remember at the beginning of this segment, we talked about how variance or variability in general is tied to reliability. And so if we have variance, we can relate it to how consistent our data set is or how consistent our values are. So the higher our number is for variance, the lower the reliability is. In other words, the lower the consistency of our values are. They change quite a bit. However, if the number for variance is smaller, that indicates a higher reliability, that our numbers are much closer together, they're very similar, they're very much more consistent. And so we'll have higher reliability. So smaller variance equals higher reliability, larger variance equals lower reliability. Now it's important to note here that when we talk about variance and reliability, that it's relative, that there isn't a particular number that says it's high or low reliability. It's all dependent upon the context of our values and the range of the scores. And so we can't just look at a single number and say it's high in reliability or low in reliability. We usually have to compare it to something. So one set of values may be more reliable than another, therefore they have smaller variance. But it's always in comparison. So it's never one value by itself. It's relative, it's comparative to the scale and to other variables. Now there's a particular problem with variance, and you can probably figure it out what it is already when we said squared deviations from the mean. We don't typically talk in terms of squared deviations. Additionally, once we square it, our variance is now on a different unit of measurement than our raw data or original values. So when Timmy gave his ratings of appreciation, they weren't in squared units, they were in unsquared units. And so with variance, we can't make a direct comparison to the original values or the mean of the original values in that variance in terms of squared units. And so it's no longer on the same scale of measurement or the same units. And so we need to take our variance and we need to square root it. When we square root our variance, we end up with what's called the standard deviation. The standard deviation is the average difference or the average deviation from the mean. And so it's in the same units as the mean, it's in the same units as the raw data, as the original data, and so the standard deviation becomes a better comparison point when it comes to variability. Alright, so our symbol for standard deviation is sigma. You'll note here that the formula is pretty much the same as variance. There's only one difference. The one difference in the formula is that we're taking a square root. So we calculate variance, and once we have variance, we just take the square root, and that gives us the standard deviation. So just remember, and students sometimes get confused, just remember that if we have lowercase sigma, and it has a square on it, so it's sigma squared, we're talking about variance. If it just is sigma, then we're talking about standard deviation, which makes sense because if you have sigma squared and you take the square root, you're left with just sigma. And so sigma is standard deviation, sigma squared is variance. Standard deviation is the average distance or difference from any value, any particular value, from the mean. So in this particular case, we will go ahead and take our variance of 6.5 and we'll take the square root of it. And when we do that, we will get our standard deviation. In other words, the third measure of variability that we need to discuss. Once we take the square root of 6.5, we end up with a standard deviation of 2.55. So what this really is saying is that when little Timmy rates his family on appreciation scores, we can say that the average difference of each of those measurements from the mean, in this case 7, the average difference from 7 for each one of those family members will be 2.55 appreciation scores. So it just tells us on average the spread of the data, that any one particular point or any one particular rating would be 2.55 ratings different from the mean on average. Now I should make a note here on rounding. Throughout this course, you can just round to 2 decimal places. I know the textbook says to go to 3, but there's no reason to go to 3 here. I think 2 is sufficient. So when you're rounding to 2 places, you'll go 3 places past the decimal point. If that third place is 5 or higher, you will round up. If it is 4 or below, then you will round down, and so in other words, you won't make a particular change. So here we have 2.55. If we were to originally take the square root of 6.55, we would have ended up with 2.549. We would round up to 2.55 because that third decimal place is greater than 5. So here is why having a measure of central tendency and a measure of variability is important to statistics. That if we have a measure of central tendency, in particular the mean, and we have a standard deviation, our measure of variability, then we can estimate the normal distribution of the data in the population. And so note here, this is not a correction. We talked about correcting for skewness earlier with squares and square roots. That is not what this is here. What this is saying, for the purposes of statistics, that we need a normal distribution. That's what's being modeled. And so if we have a mean and a standard deviation, we can approximate that normal distribution, that perfectly normal distribution that's needed to meet our assumption. Now, we'll always know the underlying data is not always perfectly normally distributed, but we will use the model of that underlying data being normally distributed. So we will make the assumption the data is normal distributed, even though we know it's not going to be exactly normally distributed. What we'll say is it's close enough, and we'll model the data using the normal distribution. So let's go ahead and use our communication salary example to estimate the normal distribution of communication major's salary for the year 2005. If you remember, we had a mean of 42,500. Now, we didn't do the calculation together, but I'll just tell you what the standard deviation calculation was. It was 6,700. So we can expect on average any one graduate with a communications major's degree would deviate from that mean on average $6,700. So I can go ahead and draw my frequency polygon for communication major's salary for 2005. So I would just draw that bell curve. I'd put a line right in the middle that represents my measure of central tendency. In this particular case, it represents the mean. So we'll say that point is $42,500. Once I have that point, I can then add and subtract a standard deviation in each direction. So I can add to 42,500, I can add 6,700, and one standard deviation above the mean would be 49,200. If I subtract 6,700 from the mean, 42,500, I would get 35,800, and I would say that is one standard deviation below the mean. And what that does is that creates a range of where I would expect most communication majors to fall a year after graduation when it comes to their salary. So I would expect that most communication majors would have a salary between $35,800 and $49,200. In particular, I would expect that 68% of communication majors would have a salary within that range of $35,800 and $49,200. Now, you don't need to remember the percents under the normal distribution quite yet. We will memorize those in Module 2, but just realize that the normal distribution tells us a particular percentage of the population that falls within standard deviations from the mean. So let's go ahead and add another standard deviation and subtract another standard deviation from what's already on our graph. And so we can take 49,200 and we can add another 6,700. And that would represent two standard deviations above the mean. In this case, $55,900. Now note here that the line on the y-axis drops from what it was from the first standard deviation and also from the mean. That's telling us that salaries of $59,900 don't occur very often. Alright, so in the negative direction, we can take 35,800 and we can subtract 6,700, and that would give us two standard deviations below the mean. In other words, a salary of $29,100. And note here again that the line on the y-axis is again very low, and so that would indicate that it doesn't happen very often. The frequency is low for salaries that are $29,100. And so we can keep adding $6,700 to each standard deviation in order to fill out our normal distribution. So if we wanted to go 3 standard deviations above the mean, then we could take 55,900, add another 6,700, in other words, add another standard deviation, and that would give us 62,600. Now this wouldn't happen. This would be a very rare event. Again, you see that by the line, how it's dropped to it's almost touching the x-axis now. That tells us that that is very infrequent. The same thing in the negative direction, that we could again subtract 6,700 from 29,100, and then we would get the value of 22,400. This would be 3 standard deviations below the mean. It would represent a very infrequent salary, not a salary you would typically expect from a major, but one that is possible. This just doesn't happen very often. And so once we have our mean and our standard deviation, we can create a normal distribution that is divided by the mean in the middle and the standard deviations to give us an indicator of where we would expect most, in this case communication majors, most of what their salary would be a year after graduation. And that becomes very informative. We can say that most communication majors are going to make between 35,800 and 49,200. And that few, so not as frequent, fewer or rarer, would make above 49,200. And very few, and again another rare occurrence, would be below 35,800.